All right, so we continue our journey a little bit here, and we have reached now binary block codes. And these, in this course, we use them for doing error detection. They can also be used for error correction, but we haven't talked much about that. The idea is that we have some bits coming in to this block encoder, and there's some bits coming out. The number of bits out is n, and n is greater than k. So there are more bits coming out than in. The ratio between these two things is called the code rate. Yeah, and there is a bunch of other things here. Systematic codes, which we use very often in practice. Then the code words have a special structure, namely that the first k bits here is equal to the input. And then we have some extra check bits or parity bits at the end. So then the block encoder basically copies the input and then adds some control bits to this. So this is used, for instance, when we do CRCs and internet checksums and so forth. This is the principle. Right? There are some properties of codes, the number of this Hamming weight and Hamming distance, which are basically a Hamming distance between two binary vectors is that we count the number of positions in which these two binary vectors differs, which turns out to be the Hamming weight of the modulo 2 sum of u and v in this case. So XOR modulo 2 works like this. Critical thing for codes is the minimum distance. So it's the minimum Hamming distance between two unique code words in the code. And this tells us something about the ability of the code to correct and detect errors. So if C is the transmitted code words, then the received pattern is a C plus an error pattern. And where the error pattern has ones in the positions where there are errors and zeros where it's no errors. So the Hamming weight of the error pattern is the number of errors that occur in the code word. And then a receiver declared that no errors have occurred if the received pattern is a code word. That's how we do error correction. So this is an important principle for error detection. Right? So this is what we do. If the receiver should figure out or make a decision whether the string of bits is an OK string, that there has been no errors, or if there have been errors, the only sensible decision the receiver can do is to look at these sequence of bits and determine, is it a code word or not? Okay, because the receiver knows that only code words have been transmitted. So for sure, if the received bits are not a code word, then an error has occurred. However, the opposite is not true. So if the received bits is a code word, we cannot infer that no errors have occurred, because what we can receive is a code word which is not the same as what we transmitted. Okay, so basically the error pattern can be so particular that it goes from one code word to another code word, and these errors are undetectable. So that's just a fact of life, I guess. But anyways, if we have a code which has a certain minimum distance, then we know that we can find all error patterns with a weight which is less than the minimum distance. Okay, so we want the minimum distance to be fairly large for these codes. And the reason for that is that it's more probable to have few errors than many errors when we transmit over a noisy channel. Okay, yeah. So basically, if C is the transmitted code word, then E is detectable if C plus E is not a code word. And the opposite is also true, that E is not detectable when C plus E is a code word. So we can detect many errors, but not all of them which have weight which is larger than the minimum distance. This is also true. So the minimum distance is not the end of the story, but it tells us something about how to pick up pretty probable error patterns, which a few errors are per code word. So good code, high minimum distance, high rate, low encoding and error detecting complexity, and ability to detect likely error patterns. Okay. So common ones is the single parity checkcode, internet checksum, and CRCs. So we talked about all of those. ARQ protocols. So now we're moving up the stack in a way. So we talked about the physical layer and how to design pulse amplitude modulation, how to process that, Nyquist pulses, everything. And then we have made a decision on our bits. Okay. These bits might still be an error. And we don't want to deliver service data units which are in error. So how can we clean this up? And one way to clean this up is to use ARQ protocols. So ARQ protocols are used to provide a service that delivers packets in order, without errors, and without duplication. Okay. So these three things are important. So the basic elements of an ARQ protocol is that we need some error detecting code, and that is basically to figure out that the service, whatever we receive, has not been affected by errors, otherwise we throw it away. We need sequence numbers, and that's basically to keep track of everything so we can deliver things in order. We also need acknowledgements, and that is to inform transmitters that receivers have received the data they transmitted. There are different ways to do access, we will see. We also need a timeout mechanism, and this is for the transmitter to eventually determine or decide that something has gone wrong if it hasn't received an acknowledgement in time, and then to do a retransmission of the data. And then we need some buffering of both the sender and transmitter for this to work. Okay, so these buffers are called send and receive windows. So the send window, what is that? Well, it's basically a buffer that stores a bunch of packets that are currently under transmission. So packets have sequence numbers, and these sequence numbers are m-bit numbers. So in this case, it's a number from 0 to 15, so that's 4 bits allocated to the sequence numbers. So we need to reuse that, right? Because we cannot keep on, the sequence numbers is part of the header, and we would like to limit the number of bits in the header. So these are always limited to a certain number of bits. Anyways, in the send window, what we do is that when we get new data from above, what we do is that we push that into the buffer, we slap on a sequence number, and we transmit this over the channel, and then wait for an acknowledgement. So if the send window looks something like this, the oldest sequence number, the oldest packet has sequence number 13 in this case, and then we have transmitted 14 and 15. The next one we will transmit will have sequence number 0, just because we reuse sequence numbers. So when the next service data unit arrives from above, we form a packet with sequence number 0, we transmit this, and we put this into the send buffer, send window. And then when the next one comes in, it's sequence number 1. So we keep on doing this until we have filled out the entire send window, and then we stop, right? We won't accept any new packets from above. Okay, these packets which are under transmission are called outstanding packets. So just the terminology. So these are outstanding packets. And we can think of these as packets which the transmitter has sent, but does not know the fate of yet. We don't know if these have arrived or not. Okay. Acknowledgements. So a transmitter sends acknowledgements with an acknowledgement number. So this is sort of like a sequence number in the ACK frame. Then depending on the protocol, this ACK with a certain ACK number can have different meanings. So in stop and wait, for instance, we acknowledge the packet which is older than the packet with sequence number equal to the ACK number. Okay, so I'll show this graphically on the next slide, but this is what's going on. Go back in, we acknowledge all packets which are older than the packet with sequence number equal to the ACK number. So here we use these cumulative ACKs. And for selected repeat, this acknowledges one particular packet, namely the packet which has sequence number equal to ACK number. So it's a little bit different interpretation of these three cases. More or less, stop and wait and go back in has the same type of interpretation, while for selected repeat it's another interpretation. And also, when it comes to selected repeat, there is a bunch of different implementations of this. So when you read about this in other books, you might get other information. But this is the way it's presented in our book. That's why it's like this on the exam, for instance. Right. So we have a state variable in the send window, and this is updated when an acknowledgement arrives. And when SF increases, we say that we slide the send window. Okay, meaning that it's updated doesn't mean necessarily that it changes, but it could change, right? It depends on which ACKs arrive. And for stop and wait, we use the notation S last rather than SF. So please be aware of this slight change in notation between these two protocols. Okay, so for instance, if we have a send window that looks something like this, and we receive an acknowledgement with acknowledgement 9, this means if it's cumulative, that means that it acknowledges all packets which are older than the packet with sequence number 9. So if we get an acknowledgement with acknowledgement number 9, it means that the receiver says, okay, I received 8 and 7. Okay. I still have not found gotten number 9, which means that the send window can be slided, but we need to keep number 9 because this has not yet been received. Okay. If it's non-cumulative, if we get the same type of acknowledgement, it just means that, yeah, I received exactly 9. So you see the difference here? Here in this case, we have not received 9, but in this case, we have received 9. In this case, we have received everything which is older than 9. In this case, we have only received 9. That's the interpretation of the ACK. So it's a little bit different from protocol to protocol. Okay, stop and wait is 1-bit sequence numbers. You know, you've done this in the project, so I think you know this pretty well, right? The only thing which is here is it's a 1-bit send 1-bit sequence number, send window size 1, receive window size 1, and this is the logic essentially. Go back in. The only difference is that we have from stop and wait is that we have a send window which is larger than 1. So if we have n-bit sequence numbers, we can have a send window which could have a size up to 2m-1. It could be smaller, but this is the maximum size of it. Receive window is still size 1, and then it works like this. So the thing is with go back in is that we have a single timer that keeps track of the timeout of the oldest outstanding packet, and whenever this timer expires, we retransmit everything that we have in the send window. Yeah, that's how it works. For selective repeat, we have a send window and a receive window size which are equally large, 2 to the power m-1. So if m is equal to 4, for instance, is 2 to the power 3, we have size 8 in both transmit and receive. Okay. Then the logic is slightly different here, and that has to do with the interpretation of the acknowledgement. then we talked about the different, why we have three protocols is because they're differently good in different situations. So I won't have time to talk about that now, but you can go back and look at the slides. Go back very, very quickly. Stop and wait is the simplest. Okay, so if nothing else, one should use that. However, stop and wait is not very good when we have long delays over the channel. So when the delay bandwidth product is high, then we go to go back n, and then we get better performance. However, go back n is not good when we have significant number of errors on the channel. So if we have a large delay bandwidth product and also a high probability of error, then we go to selective repeat. Okay, so under benign situations, we use stop and wait. Under difficult situations, we use selective repeat. In the middle, we can go for go back n. Again, so this how to measure efficiency of these ARQ protocol, we use this effective data rate and efficiency that we talked about earlier. But I have a plot of this also, if you like. So if this layer is implementing the ARQ protocol, it will send then information frames and ACK frames back and forth here using a data rate which is R bits per second. Physically, R bits per second is provided by the layer below. But anyways, if this is R bits per second, this back and forth here enables the layer above it to send its service data units here, send its protocol data units, which happens to be the service data units for the layer below it. Anyways, that's how it is. Back and forth here with some effective data rate. And then the efficiency is the effective data rate divided by R in this case. So whatever bit rate we have here, how much of that can we conserve for the layer above it? That's the efficiency. And then there's some terminology here on frame sizes and so forth, which is not super important here, but concepts that should be clear, I hope. Medium access control is also part of the data link layer. So, but we talked about ARQ protocols. These are found in the data link layer. They're also found at other places in the stack at higher protocol layers. The medium access control, however, is only found in the data link layer, and it manages sharing of a common medium. So when you have several transmitters that is competing somehow for the same medium, then we use medium access control. So it's a sublayer of the data link layer just above the physical layer. And then out of all of these methods, there are static and dynamic. And of the static is basically just one subfamily of this is called channelization. For the dynamic, there is coordinated and random access. And there are some examples here. How to think about medium access is that we have a number of transmitters, and we call them stations here. Now, one thing that changed from the books here is that this one was in previous books. This was called M, right? But you know that really doesn't matter. It should be clear from context if it's M or N, right? So you know, whatever, right? You can figure it out, I'm sure. But anyways, we have a number of stations. All of them are producing a number of frames per second that should go over this shared medium. The total number of frames per second, or frames per frame duration, or frame per something, is indicated by this lambda, which is the sum of the lambdas. So what goes down here, say here, this is new packets plus retransmission packets. Right? So whatever goes down here, it's not always new packets. It could also be retransmission packets and so forth. But anyways, all of these packets needs to be shared over this channel. Okay, so if we have some frame duration and some frame length, then we have a data rate which is available. These are related through the data rate of the medium. So R is equal to NF over TF. So if one knows two of these, one knows the third, right? The offered data rate is the aggregated load, aggregated data from all the users. So it's lambda, the total number of frames which are generated per second, times NF, which is the number of bits per frame. So that gets in bits per second. The load is how much the offered traffic is in relationship to the capacity of the medium. So it's lambda times NF divided by R. And this offered load here could sometimes be supported by the medium and sometimes not. There is a maximum value that the medium can support, or basically it depends on how smart the medium access control is. Anyways, the throughput is the service data rate from all the users, which is RU bits per second. So how to think about this is that out of all the packets which are pushed down here, some of them are of all the packets which are pushed down here, not all of them. Okay, sorry. There is a frame coming down here, and then eventually it will come up here, right? But it might be that it goes over this and it's colliding. It has to be retransmitted. There could be a few things going on here, but at some point it goes down here, and at some point it goes up here, and it takes t seconds to do this. So then the useful data rate from all users is a measure on how many frames are delivered per second multiplied with the number of bits per frame. So this is some useful data rate over this medium. There might be a lot of bits being transmitted here, but not all of them are useful in the sense that they are actually delivered, because there might be retransmissions and so forth. Anyways, the useful data rate, RU, if we can measure that in bits per second, then the maximum load which is supported by this medium access control scheme, which is also known as the maximum efficiency, is rho max, is the maximum value of this useful data rate divided by R. Now, the longest propagation time of this medium depends on the length of the medium and then the propagation speed of the medium. And once we have that, we can compute the normalized delay bandwidth product, which turns out to be a critical parameter in the efficiency of these schemes. Okay. I don't have time to go through all the equations here, but if you go back and look at Aloha and CSMA and these different types of schemes, there are some efficiency calculation formulas for these. Yeah. So the delay bandwidth product is key parameter, and the idea that why it's like this is because when we want to coordinate sharing of the medium, we need to use the medium to do this. And the more delays we have of the medium, the more difficult it is to do this in a good way. For Aloha, which is one of these uncoordinated schemes, random access schemes, we transmit the frame, wait for an ACK. If there is no ACK, then we back off and retransmit. Super simple protocol. So it's almost like stop and wait, except that we have this back off, random back off. Normalized throughput for this is, according to this equation, and then we did some simplified analysis, and then we figured out that the maximum throughput, normalized throughput, is 1 over 2e for the unslotted and 1 over e for the slotted one. So e here is the Euler's numbers, this 2.7 something. We can improve on Aloha by using carry sense multiple access. So basically, before transmitting, we listen to the channel. If the channel is busy, we wait, and then we transmit at a later point. And the waiting here, what to do when it's busy, depends on the different variations of CSMA, so we can do different persistence schemes. I won't go through this in detail, but just so these are the important variations of CSMA: 1 persistent, non-persistent, and p-persistent. I'll let you go back to this, but the overall conclusion is that we have better throughput than ALOA, but only if the delay bandwidth product is sufficiently small. So for very large delayed bandwidth product, we might as well go with ALOA. We don't gain anything from carrier sensing. Controlled access and channelization is basically, we have these reservation protocols. So it's a two-stage thing. So before we transmit data, we organize the transmissions. So we have cycles. And a cycle consists of a reservation interval plus data. Reservation is done in mini slots, so shorter packets, and data frames is done in slots, longer packets. And the reservation interval is used then for the users to reserve slots if they have data to transmit. Polling is another way to do a controlled access. So you can look at the slides to figure out the different ways this could be done. Channelization, a channel resource. It's a rectangle in time frequency plane. So you have, I don't know, some time and some frequency, and we want to split this. So if we do time division, we split the time into time slots like this, and each user can use it for a certain time. If we have frequency division, instead of the blue ones, we divide up the frequency domain into frequency channels. And in practice, we often use some type of hybrid, which is a hybrid between TDMA and FDMA. So we have here squares in the time frequency domain that we hand out to the different users. So this hybrid is used in LTE, for instance. Yeah. Then there is also something called code division, where we don't split up time or frequency. We just use signals which are uncorrelated with each other, but overlapping in both time and frequency. These exist. There's nothing strange about them, but there is no particular advantages that we get more channels by using code division compared to frequency division or time division. So all of these generate the same number of channels under ideal conditions. Which one to choose depends on properties of the channel. So these are more practical implementations. And the practical implementation issues have to do with that we need to install some type of guard interval between the time slots, for instance, or guard intervals between the frequency slots here. Right? And which one to choose of time division or frequency division here depends on how much of these guard intervals we need to put in. Right? In some cases, one is preferable to the other. Right. Then, once we have done the medium access control, the ARQ protocols, and so forth, we would like to connect LANs, local area networks, and we do this with bridges or LAN switches. So we talked about that. So basically, we have a number of stations here, and they're connected to two different LANs. We put in this bridge device, and then for all the hosts, for all the end computers here, it looks like we're communicating on a big LAN. And we do that in a way where the data link layers of these nodes here are oblivious to they don't know the existence of this one. So the existence of the bridge is transparent to the hosts. And this can be done by the bridge using this backwards learning or adaptive learning, or has a few other names. But essentially what the bridge does is that it listens to traffic on the LANs, and then figure out where the stations are located, and then form a forwarding table from that. Yeah, the problem with this, problem with this learning algorithm is that it doesn't work when we have loops in the physical topology, and then we need to implement this spanning tree protocol or somehow disable the loops to form a logical topology without loops. So this is among the last things we did in the course. The last thing we did in the course was to talk about security. So we talked about confidentiality, integrity, and authenticity, what that means. Then we talked about two different ways to do cryptography, symmetric and asymmetric, and the pros and cons with these. And both of them are used in practice because they have different advantages and disadvantages. And basically one difference is that asymmetric crypto is much more computationally demanding than symmetric ones. The problem with symmetric crypto is essentially key distribution, how to do that in a smart way. There are also some other disadvantages with symmetric crypto. But so common schemes combine symmetric and asymmetric cryptography to sort of gain the best of two worlds. So we talked about that, and you can look at the slides there for more information about this. So, yeah, I don't know if you are tired. I'm getting tired of talking here. This was, you know, way too much information into short time, and the scary thing is that it's actually more information about the course than we could possibly talk about today. These were only highlights, maybe a little bit of a refresher, maybe a reminder for what things you should go back and look at. But for sure on the exam, there will be some stuff that I talked about today that will be on the exam. For sure, there will be something that I haven't talked about also. Yeah, so that's the only thing I can guarantee. Yeah, but the most important things is covered what I said today. Right. Any questions on this? No? Okay, so now many of you are selecting master programs in the fall, and some of you might be also interested in what is available in this general area of communications. So let me spend a few minutes on saying this also. So there, first of all, communication is everywhere, right? So it's very nice, I think, to take one of these courses to get a little bit of feeling for what's going on, so you can at least understand when people talk, communication experts, when you talk to them, what they actually are talking about. So whatever you do, you're probably in any engineering field, I think you would use communication as part of your solution somehow. Now, if one wants to concentrate more on learning more about communications, then depending on what you prefer in the protocol stack, there are different master programs that are more or less suitable for this. So if we have the highest abstraction level, there is this MPNet, Computer Systems and Networks. So this is more, would say, computer engineering, computer science, programming, protocols, how to do services on a higher layer, right? Then we have MPCOM, Masters in Communication Engineering, which is dealing with the lower layers here. Physical layer, quite a lot, a little bit of data link, maybe touching on network layer, but has its emphasis here. Then if one is more interested in hardware, then there is this Masters in Wireless Photonics and Space, which deals with hardware basically for wireless in many aspects, both for communications but also for sensing, how to measure things from satellites, whatever, right? Then if one interested in so this is more the analog part, I would say. If one is more interested in digital hardware, there is this MP in embedded electronic and systems design. So this is sort of like putting these into the protocol stack, if you like. Then I encourage you to go and listen to all the presentations and figure out where you want to be. I think work market is good in all of these fields, so depending on what you want to do, basically. If we look at MPCOM, the one that I know most about, then these are marketing slides, right? Enabling the interconnected world. Sounds great. So let's do it, right? So basically, as I tried to say, ICT systems is everywhere. And enabling technology for this is communications, among other things. There are career opportunities in the Gothenburg area, so if you want to go there, you can go for the telecom, 5G, 4G companies. Ericsson and Huawei have activities here in town. Then there are users of this, like Volvo Cars, Volvo Trucks, Zenuity, Saab, ABB, Ruag Space, Autoliv, Camcom, bunch of different consulting firms of various sorts. So this is not an exhaustive list. So there's quite a lot of diverse industries here that are using, that are hiring engineers that comes from MPCOM. And obviously for PhD studies at Chalmers and elsewhere, this is also a suitable program. So depending on what one wants to do, there's specializations in mobile communications, Internet of Things, optical communication, smart society, whatever, right? You can read more about this in the folders at mpcom.se. The reason why I'm pushing this a little bit is that people in my group and myself have been involved in this master program. This is what I know the best. But again, you should listen to all what they have to say. Is this interesting for me? Is there nice job opportunities afterwards? What are my plans for the future? And then pick something that connects with this, right? But you knew this already. So any questions before we end? No? So anyways, it's been fun having this course. I hope you enjoyed it too, and I wish you all luck on the exam. And it's still a week to study for that. So me and Shoaib will be around a little bit. We're rebuilding the offices now, so Shoaib moved his office. I don't know if you noticed this, but if he's not in the office that he used to be because he had to move, it's in the same corridor as I am, a few doors away. But email is probably the best, right? We'll be happy to answer your questions as much as we can. All right, so good luck.